Welcome back to Science Click. Today, the Mathematics of General Relativity, Part 8, Summary and Applications. To conclude this series of videos, we will summarize all the concepts by proposing a catalogue of the different possible solutions, and applying them in several concrete examples. We'll be able to calculate the time dilation for an astronaut in the space station, determine the equations that govern the motion of an object falling towards the sun, and even explain the behaviour of light around a black hole. To begin with, let's summarise together the different steps that allow us to solve a problem in general relativity. The first step is to determine the space-time geometry in which we want to solve our problem. This means choosing the metric that we want to use. In an empty universe, we will use the Minkowski metric, the flat space-time of special relativity. Around a spherical and static mass, we will use the Schwarzschild metric. This metric is the most practical because it is simple, but can still model many different situations. It can describe a planet, a star, or even a static black hole. There is also a range of other more exotic metrics, such as the FLRW metric, which describes a homogeneous universe, the Morris-Thorne metric, describing a non-gravitating wormhole, or the Kerr metric, which accounts for the rotation of a black hole on itself. The second step is to choose the coordinates that we will use to describe our problem. Depending on the situation, some coordinates are more appropriate than others. The Minkowski metric is most often expressed with Cartesian coordinates, which reflect its linear structure. For the Schwarzschild metric, we choose spherical coordinates to exploit the symmetry of the central mass. That said, our problem may not correspond to any of these usual solutions. And in this case, we will have to determine the most appropriate coordinates, start directly from the Einstein equation, and integrate the different curvature tensors to find an expression for the metric tensor. This process turns out to be extremely complex, and usually requires approximations and computer simulations. Once our coordinates have been chosen, the third step is to analyse the symmetries of our problem to reduce its number of dimensions. For example, to describe the motion of an apple falling vertically, we only need one dimension of space along a single axis. Likewise, for an object in orbit around a spherical mass, symmetry tells us that its trajectory is confined within a plane. The object has no reason to leave this plane on one side or the other. In this situation, we can align our coordinates with this plane, reducing the problem to 2 dimensions of space. Finally, once we've chosen a metric and coordinates, we can seek to find the solution of our problem. For solving the problem, we have 2 possibilities. On the one hand, we may want to find the components of the velocity of an object through space-time. For example, we may want to express the temporal component, the rate at which our time passes compared to its proper time. In this case, we use the fact that all objects in the universe move at the speed of light. The norm of the velocity vector must always be equal to c, which gives us an equation relating the components of the velocity to each other. On the other hand, we may want to determine how these components change over time. In other words, how the object accelerates through our coordinates. This way, we can describe whole trajectories through space-time. For example, we might want to determine the motion of an apple falling towards Earth, or the trajectory of the Earth around the Sun. In this case, it is necessary to calculate the Christoffel symbols, allowing us to use the geodesic equation. In the case of the apple, for example, the equation tells us that its altitude coordinate undergoes a negative acceleration. It falls. To sum up, we start by choosing a space-time geometry to describe our universe. Then we reduce the number of dimensions using the symmetries of our problem. And finally, we use either the norm of the velocity to relate its different components, or the geodesic equation to determine the trajectory of an object. With this method, we will be able to solve a large number of physical problems step by step. Example 1. Time dilation. In this first example, we want to determine the time dilation for an astronaut in the space station. To solve this problem, we will follow the different steps that we described previously. First, let's choose the metric that best fits our situation. We can consider that the Earth is a sphere, and we can neglect its rotation on itself, which is very slow against the speed of light. In this simplified framework, space-time outside the planet can be modelled by the Schwarzschild metric. In its most intuitive form, the Schwarzschild metric is expressed with spherical coordinates, measured from infinity. We imagine observing the planet from a great distance, and measuring the time t on our clock, the altitude r of the station from the centre of the Earth, and the angles theta and phi. The metric tensor then takes the following form. Once the metric tensor is expressed in all 4 dimensions, we can try to reduce it, taking advantage of the symmetries of the problem. To simplify, we can assume that the station follows a circle around the Earth. Aligning our coordinates on this circle, we no longer need the angle theta because the station orbits in a plane, and neither do we need the altitude r, which remains constant along the circle. We can thus get rid of the rows and the columns that correspond to these 2 coordinates. The position of the astronaut in spacetime can be described with only 2 numbers, the time t and the angle phi. Finally, once the metric tensor is expressed in a coordinate system, we can move on to solving the problem. The time dilation that we want to calculate corresponds to the ratio between the rate of our time, t, and the astronaut's proper time. In other words, it's the temporal component of its velocity, the rate at which the coordinate t increases as proper time goes by. To determine this temporal component, we will use the norm of the velocity vector. In spacetime, all objects move at the speed of light. The astronaut moves both in time and space, but his overall speed in spacetime is always equal to c. The norm of a vector in general relativity is obtained using the metric tensor, the generalized version of the Pythagorean theorem. Expanding the sum and using the Schwarzschild metric, we obtain an equation which directly relates the 2 components of the velocity. On the one hand, the angular velocity, the rate at which the angle that the astronaut forms increases around the Earth, and on the other hand, the temporal velocity that we want to determine. Rearranging the terms and using the fact that the orbital velocity of the station is equal to its angular velocity multiplied by its altitude, we finally obtain the expression for the time dilation that the astronaut undergoes compared to a distant observer. For the International Space Station, we estimate a dilation of 1 nanosecond for each second of proper time. The astronaut's time passes slightly slower than that of the faraway observer. Example 2. A vertical fall. In this second example, we want to describe the fall of a satellite towards the Sun. We consider a vertical fall, and we make the approximation that the Sun is spherical and static, and can therefore be described by the Schwarzschild metric. We will use the same coordinates as in the previous case. We observe from a very far distance and measure the time t on our clock, the altitude r between the satellite and the center of the Sun, and the angles theta and phi. As the fall is vertical, the angles theta and phi do not vary, and we can already get rid of them. The position of the satellite depends only on its altitude and time. In this example, we will not be interested in the velocity of the satellite, but its evolution. We want to determine the acceleration of its coordinates. To do this, we start by calculating the Christoffel symbols. In the Schwarzschild metric, with these coordinates, the Christoffel symbols take the following form. Once calculated, we can inject them into the geodesic equation. The geodesic equation gives us two relations. It tells us the acceleration of each coordinate describing the satellite. On the one hand, its temporal acceleration, and on the other hand, the acceleration of its altitude. These two formulas allow us to integrate the trajectory of the satellite with respect to proper time. As long as we know its initial velocity, we can calculate its acceleration, and thus the way in which the vector will change at the next instant. To go further, it is possible to interpret these equations in a more elegant way. The first equation in particular can be put in a different form, which indicates the conservation of a certain quantity. This quantity is proportional to what we call energy. In the Schwarzschild metric, the energy of an object depends on its altitude and its movement through time. Example 3. A ray of light. To conclude this series of videos, we will describe together the trajectory of a light ray around a black hole. In the case of a static black hole, space-time is once again described by the Schwarzschild metric. In general relativity, light is a very special case, which we have to treat differently. To understand why, let's go back to the fundamentals. We saw in the previous videos that an object traces a world line through space-time. This world line can be graduated with intervals of equal length. These intervals along the curve allow us to interpret it as a movement. This is called proper time. As proper time goes by, the object moves through space-time, and we can define a space-time velocity vector. But unlike matter, light does not travel any distance through space-time. 2 points along its world line are always separated by a distance of 0. Therefore, we cannot define a proper time for light. We need to be more careful when dealing with light, because it's not possible to define a proper velocity vector for it. To solve this problem, we have to define a new graduation specific to this light ray. This new graduation is called an affine parameter. Unlike proper time, the affine parameter has no real physical meaning. It does not measure any distance in space-time. It is simply an arbitrary graduation which will serve as a mathematical tool for equations. Thanks to this affine parameter, we can define a sort of velocity vector, and thus use the geodesic equation, which remains valid. On the other hand, we will also be able to use the norm of this vector. But unlike a real velocity vector, this artificial vector that we have created especially for the light ray has 0 length, as light travels no distance. Its norm is 0. Being careful to account for this difference, we can still apply the same reasoning as before and obtain the geodesic equations which govern the path of light rays along their affine parameter around a black hole. These equations tell us that light is deflected around the black hole, which acts like a gravitational lens.